Okay, you should be able to hear me, and of course, to make this work well, you can tell me in the Discord if you can actually hear me. That is good. With that, let's kick things off with real flavor and style. And here we are. Hello, this is live. And you see Ramin is, and so on. We can hear you and have sound, and I can see all this. So this is like next to that screen, and I can see it reasonably well. So if there's anything, you can give me a shout or whatever else. And with that, let me switch to this one here. And what's happening here is you see this is chapter 4. So chapter 1 was sort of an introduction, and then we had the set cover, and then we had the packing problems. And now we'll start Turing problems. And of course, some of you may still remember Algorithms and Data Structures 1, the very first lecture ever. And there was a royal blue background. And I took you to that Mediterranean scene. There was this very, very smart and clever person here on this little island in Western Greece. And that person was in demand and was asked to travel. And of course, that meant solving some problems here in somewhere further east. Went there. Tried very hard for 10 years with his buddies to solve that problem, to crack that problem, really. Lots of brute force attempts, and then he came up with this really smart solution of getting in there, and it's something we still remember today because there's like a way of putting in a backdoor Trojan, whatever. And of course, that was Odysseus, and you know the story of how that continued. He wanted to go back, dropped off a colleague, then he was almost home. He just had to turn that corner, and then he was a little blown off course. And being blown off course meant that he was busy in the Mediterranean for quite a while, seeing all those things, and that was before there were t-shirts for sale. And he got back just in the nick of time. This was actually 20 years later, 20 years after leaving. He spent 10 years in laying siege to Troy, and then he spent another 10 years traveling the Mediterranean to get back. And he came back just in time to save his faithful wife from trouble. And of course, what happened, we know that she may have said, like, couldn't you make it any faster in 20 years? And 10 years for the trip, which of course is something, let's see what happens here. Click that button, so let's forget about that, and let's forget about the Mediterranean. Let's look at this and connect these dots, and the question is, isn't there a better tour of doing this? Can't you make it any faster? That is one of the earliest instances of the traveling salesman problem. The traveling salesman problem, of course, as you know, and if these slides look a little old, it is because they are. They are about 20 years old. Man still lost directions. Yeah, well, you know, there's that. Of course, by now we have apps that come very often with female voices if you want to use that. But GPS is another issue, and we'll talk about satellites another time. So what you have in these old vintage slides that I've used before, and I was deliberately using those because it may bring you back to your first semester in Algorithms and Data Structures. You're given a graph with edge lengths or edge weights like this, and you want to find in this graph a shortest round trip. A shortest round trip could look like this. So you have a set of edges that visits each vertex once and returns to the origin. And when you do that, so it means that you have a sequence of different locations. In the sequence of locations, there's always every vertex has a predecessor and a successor, and that is an edge, of course, between, and that incurs a cost. So what you're looking for, technically speaking, is you're looking for a permutation of the n factorial different permutations that has minimum total edge length. And the thing that typically we look at when we're looking at one of those optimization problems, Karp in 1972, almost 50 years ago, he proved that this problem is in fact NP-hard, which is remarkable because 1 year before there was Cook's theorem that said there are these problems which are hardest in the class NP, and he had the satisfiability problems, and Karp said, load. There's a bunch of optimization problems, understandable, graspable, not abstract logical problems, but a lot of these real-life problems which are in fact NP-hard. And the traveling salesman has been probably one of the most prominent one. Some people have called it the Drosophila, or fruit fly of optimizers and algorithms people, because it is a problem that is really easy to define and understand. And as you see, it has classical roots as well, but it is still difficult and hard. And obviously, there's also some real-life context. So yesterday, today is Tuesday, yesterday we submitted a big proposal for something dealing with quantum computing, and so there's people who think that quantum computing will be able to do even better and faster and all this. And what typically shows up in this, even by people who don't do algorithms, like, yeah, the traveling salesman problem. So, of course, round trips. So this was classical. I mean, Mediterranean, old Greeks and all these sorts of things. New world. In the new world, there's, of course, things that XKCD does, and it wouldn't be a proper lecture if there wasn't an XKCD somewhere. And so there are a few things. So, I mean, you can see that's the continental US, the traveling salesman problem. Brute force solution is O of n factorial. O of n factorial permutations, right? So you have these, you check these. There's something like, it could be n times n factorial, because, you know, you take each one of them and then you check their solutions. But there's some symmetry behind this, a rotational symmetry that saves you an n. So you save an n, you spend an n. It's something like n factorial. Now, there are some ways of doing it a little faster. And this salesman, so you see, this is really an old classic salesman, like from the 50s. You may know this Miller novel, Death of a Salesman, and so on. I mean, this is, who in his mind would wear a hat like this and drag around a suitcase like this? But he's sort of drawing this, and he's doing something slightly more clever, because he's using dynamic programming to solve this. For those of you who remember dynamic programming, you look at partial sets, subsets, solutions, and then you try to somehow incrementally compute good solutions for bigger ones from smaller ones. And so let me wave my hands over this. Suppose you have a subset, and now suppose you have a first and a last in that subset. So there's 2 to the n subsets, and for each subset you have, you say like, okay, this is the first and that's the last, and then if you compute for each subset with a given first and a given last, that shortest tour, and you know this by enumeration or whatever, so you have a table for every subset with a given start and a given end. And then you can do an update, because then suppose you take another vertex, and that vertex could be first, last, whatever, and then you have a predecessor for this, which is sort of the first one here, and then, or the last one here if you go this way. And so you can do an update here. I mean, waving my hands over it is not important for the purposes of this lecture, but it goes to show that even doing something slightly clever, like dynamic programming instead of doing brute force, you can bring this n factorial down to 2 to the n times n squared, which goes to show that n factorial is actually quite a bit worse than 2 to the n. But 2 to the n is still bad. So there are questions of how you can defeat this and make this even better. And now one way of doing it is, of course, to use a totally different way. use modern technology and well, it could be mathematical programming. So there has been some work, and this is sort of the hover text of that particular XKCD that says, what's the complexity class of the best linear programming cutting plane techniques? I couldn't find it anywhere. Man, the Garfield guy doesn't have these problems. So we could talk to Bill Cook, his name will show up in a moment, which is a different class, a different lecture, and that will be something where that can be talked about. I'll mention a couple of things on the next slide, because the complexity of that is a totally different question. But hey, there's something else here. So the thing is about these cutting plane methods, it's a totally different angle. The angle of this is not have a worst case runtime for all instances that is guaranteed. The idea of algorithm engineering, linear integer programming, using cutting planes, solvers, special thing, is to look at individual instances and push the frontiers of where you can still compute optimal solutions as far as possible. In particular, this is this classic of 13,509 post offices in the USA. And this, in fact, what you see here, this little white line that sort of snakes across the Rockies and goes coast to coast and up and down and back and forth, that is the best solution for these 13,509 post offices. Now, we don't know how many post offices are still left and whether that is of any use to Kevin Costner. I'll mention this on later upcoming slides. But there's a fundamental difference. So you can deal with a hard problem by looking at the constants, looking at instances, trying to solve what is possible. Approximation algorithm is different. Approximation algorithms want to do for all instances, regardless of constants and numbers and so on, guarantee that whatever it is in polynomial time, you get within a guaranteed constants, worst case. So if you want, approximation algorithms are more universal and more pessimistic. So it's independent of the size. This, of course, eventually will hit a wall, but if you're smart and if you're dedicated and if you're willing to spend a lot of computing time, so this was, you see, that's more than 20 years ago. They used, come on here, 10 years of CPU time, which is a lot, enough for Odysseus to lay siege to Troy or to discover lots of interesting things and adventures in the Mediterranean. But this was really one of the big landmarks of optimization, practical optimization, and of course, theory as well. Question is, can you make it any faster? There are a number of reasons and a number of aspects. There's this particular, like, isn't there a shorter tour? And there's this slightly different for the runtime, like one meta level, can you compute this any faster? But of course, it's a hard problem. So even getting it into any time like that at all is hard enough already. So there's a way of doing it faster, and that, of course, requires a different kind of doing business, different kind of sales. So you could do it like on eBay, and then the things just come to you. There's nothing about the route. Yeah, that's a way of doing it. You can take that easily or not so easily. Now, let's look at the approximation. And here I brought you probably the easiest approximation algorithm that there is for the traveling salesman problem. And it has something to do with this. So for those of you who remember this, this was also like the first real chapter in Algorithm Data Structures 1. It's Eulerian tours, right? So you remember there was this house of Santa Claus, and you want to draw this in one stroke without lifting your pen, without duplicating any edges. And there was a particular aspect to it, which was these odd vertices. These odd vertices, odd degree vertices, are a bit of a problem, because if you have odd degree vertices, then you need to start at one and stop at the other. So it's not, if you do this, it's not a closed tour. if everything is even, so there's no odd degree vertices, then you can do a Eulerian tour, which returns to the beginning. That is interesting if you somehow manage to have a structure that has a number of properties. One of the properties is that it is connected. Another, so otherwise you cannot visit all the vertices. Another property is that it shouldn't be too expensive. So if you just want to visit each vertex once and you travel all of the edges in the graph, you may visit many edges multiple times. In fact, if you take a complete graph on all the vertices and you have, say, an odd number of vertices, then your complete graph has even degree everywhere. So if you have 2n plus 1 vertices, and you have a complete graph, then every vertex has degree 2n, which is an even number, which means, yeah, it's Eulerian. But that would be really, really expensive. So you want a substructure, and the substructure should somehow not be too expensive. And that is one of the ideas. So we're looking at these, for this really, really simple approximation algorithm that is coming up. And there's a third aspect which I'll talk about on the next animation sequence. So let's keep that in mind. And now here's what we'll do. So here's basically the algorithm, and that's where the visualization of the algorithm is happening. And we'll do a few things. We'll look at this bit by bit. So the idea is you have these vertices, and I'll draw them already with the spanning tree in a moment. Find a minimum spanning tree. Here is a minimum spanning tree for those 6 points, vertices, cities, whatever have you. And that has 2 properties here. One is you can compute it in fast time. We all know how to do this. You can use a greedy algorithm depending on what your favorite is, prim or Kruskal. And for those of you with a more exotic flavor, you could even use Chazelle, but nobody knows really how to do this property. It's very, very fancy. Most people use prim or Kruskal or something like that. And that is something you can compute. So this has been computed. Now, why is that a good thing to compute? Because I claim that an optimal tour is not shorter than this minimum spanning tree. Why is that the case? Think about that. And when you have an answer, type it into the Discord. So imagine you're traveling something on this set of points. Maybe it's points in the plane. And whatever tour you have, it must be at least as long as a minimum spanning tree. Why is that? Maybe somebody can answer that. I don't see anybody typing yet. So what is a property that a minimum spanning tree and a tour both have in common? It would be so much nicer if I could just call on somebody like Maurice or Ramin or many of the others, Florians and whoever else. Somebody is typing. Several people are typing. Let's see who's fast. The MST visits all the points. Each edge is visited at most once. All vertices are reachable, interconnected. I would like to, somehow these are all correct. The MST visits all the points. Dan, why wouldn't a matching do this? You could take a matching, right? You connect these two, you connect these two, and you connect those two, right? So that covers all the points. There's 6 points. You have 3 edges. Why is the matching such a good thing? What is a property that the minimum spanning tree has and the matching does not have? And that gets me to what Ramin was saying. All vertices are reachable, interconnected. And of course, Maurice and Dan can continue typing. Ramin, they're all connected in one set. Okay, that's true. So a minimum spanning tree, connects all the vertices, and so does a tour. A tour has to connect all the vertices. That's part of the properties of a tour. Why is the minimum spanning tree not longer than a shortest tour? So Maurice says it has a part or a path from each node to every other. Well, it's a minimum spanning tree. A minimum spanning tree is defined as the set of edges of lowest cost that connects all the vertices so that every vertex can reach every other, and that's the total minimum cost. So what we know is, one, we can compute this fast, greedy. And Maurice is saying that a Hamiltonian path would also be a spanning tree. That is correct, a Hamiltonian path. But it is a different, and this is among all the spanning trees, it is the shortest one. Now, since a minimum spanning tree is of all the sets of edges that connect all the vertices in one connected network, the cheapest one, that means a tour, which also has that property, cannot be cheaper. Okay? Okay, let's take that. And now remember, there was something about Eulerian. Now this is not Eulerian. This is a degree 1 vertex. This is a degree 3, 1, 1. So if we simply double this minimum spanning tree, come on, you can do it, double, and double these edges, magic. How expensive is that? Well, that's twice the cost of a minimum spanning tree. This is a multi-graph because some edges occur more than once. What's the cost? It's 2t. Is that Eulerian? Of course it is Eulerian because every vertex has degree 2. Now what you can do here now is you do an Eulerian tour in this graph. That's easy. I mean, you just follow the spanning tree double. So I don't even have to run through this. I think you can all see that. That's easy. Now that is not a traveling salesman tour, because when we do this, we go up here, and then we would follow this set of vertices again, and we're only allowed to visit each vertex once. So what we should be doing here, rather than visit these again, we should go to the next one and do a shortcut. So we skip all the ones where we already were. So instead of following this path, we go along here. That is not longer. That is not more expensive. Why is that not more expensive? Because of a property that geometric distances have, which is the triangle inequality. So this is an important thing. You assume here triangle inequality, and I'll leave this for your own thoughts and for the big tutorial and so on, to convince yourself that if you don't have triangle inequality, things get really messy. Anyway, so let's follow this. Then we do a shortcut here, and then we follow this. We've been here before. We do a shortcut there, and then if we do that, we do a tour by doing shortcuts, and you get this kind of thing here. We do this, and we get this kind of tour. See that? There, and these slightly fatter edges are the ones where you did shortcuts. Now, when you do shortcuts because of triangle inequality, it doesn't get longer. Triangle inequality says you may have a shortcut. So shortcut is, in fact, maybe shorter and not longer. And you see you have a tour here, which was born from a minimum spanning tree. You doubled it, so the cost was twice as much. And then you did shortcuts, which may be a little less than twice as much. And because twice that tree is not more than twice opt, you have a tour approximation. Pretty straightforward. I don't think it's worth really fretting about this too much, because it's not the best you can do. Here is a different algorithm. Let's look at this again. We find the minimum spanning tree. Okay. Bang, here's the minimum spanning tree, still and again. And now, remember, we wanted to do something Eulerian. We wanted to be able to do an Eulerian tour on some extra edges with the minimum spanning tree and then follow that into shortcuts. But in order for this to be Eulerian, we don't need to double everything. Okay, doubling all the degrees is of course an even number, but instead, when you look at this, this is a degree 1 vertex, this is a degree 1 vertex, 3, sorry, 3, that's an odd number, 1, 1. Those are even degrees, so we don't even have to worry about those. So what we can do instead is we look at those odd degree vertices, 1, 2, 3, 4. This is an even number, and the good thing is there's always an even number of odd degree vertices. Handshake lemma, if you count the degrees, every edge adds 1 to the degree of both of them, so the sum of the degrees must be an even number. And when the sum of degrees is an even number, that means the number of vertices with odd degree must be even. If it was odd, then we'd have an overall sum of degrees, which is odd, which can't be. All right, so we have an even number of odd degree vertices. We do a minimum cost matching on these, something like this. So maybe it's a 2 here and a 2 here, there's some numbers, whatever. And now when you look at this, the original black tree, minimum spanning tree, and the red edges, that is an Eulerian graph, because you just added 1 to the degree of every odd degree vertex, and just that, and so every vertex has even degree, and because it came from a minimum spanning tree, it's also connected, so that is fine. So you just look at this and you say, okay, I take this and I do a, if I want to turn that into a tour, I do the same thing again. I have a Eulerian tour, and if I visit something again that I have visited before, then we get shortcuts, use triangle inequality again, and we get a tour. Why is that cheaper? That is in fact a 1.5 approximation algorithm. And I will not completely answer this by proving a lemma and a theorem and so on, because we have a bit more on our plate today. You can show and convince yourselves that this is in fact a 1.5 approximation algorithm, because here in a nutshell is the argument. If you look at this matching, then, and you look at what an optimal tour does, an optimal tour induces a matching on the odd degree vertices, because you just follow that order, and using the direct connection may even be cheaper because of triangle inequality again. But here's the thing, an optimal tour induces 2 matchings on the odd degree vertices, because there's the ones which may be part of the tour, and then there's the other ones which are sort of shifted. So there's a set of edges, and there's another set of edges. So you can map an optimal tour to 2 matchings on the odd degree vertices, which means that the cheaper one of them is only, because triangle inequality shortcuts again, is only at most half of it. And now here we're using the shortest among all the matchings, which means that this is at most half, which is at most half of opt, so we get 1 extra 1/2. This was shown by Christofides, and there was a tech report published in 1976, another classic, which was never really published other than in this tech report, but it's highly cited and all that. Now you could also wonder, like, is this the best possible thing here? I mean, 1.5. Can you improve that? And it turns out, here's an example which shows that this estimate of 1.5 is indeed tight, because you could think of having a spanning tree which goes in this zigzag, 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 and then you have one odd degree vertex, another odd degree vertex, and you do this. So you get this length, and then you get the zigzag, 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 which means basically that you get this length again. And when you think about this, you're doing here, you're doing 2 for every vertex here on that side, instead of doing 1 for every vertex. So if you have n vertices here, you're getting, see that, you can convince yourself that you're doing 3 times that number in this zigzag, zigzag, and back up, constructed by Christofides. Whereas obviously the best way would be to just go up here, go over, go down here, like this. So instead of having the zigzag where you pick up these points, so basically it's 2 between each of these, you only get 1. So you have this n and that, n-1 or n, pretty much the same. So you get 2n instead of 3n, and so that's a 3 over 2, which happens here. Now that is a few things. It's a 1.5. It's an argument that this may be 3 over 2, 1.5. But it's also something to keep in mind, because what I'll show you next is slides of a talk that were given by a colleague not so many years ago at a big international workshop where he talked about new approaches of approximating TSP. So Ola Svensson from the EPFL in Lausanne and doing this survey. What you will see then, I will wave my hands in some places vigorously, but it will give you sort of the state of the art on approximating TSP in a number of ways. And it focuses on the 3 over 2, the 1.5 in some ways, and you'll see some things of how to get better than that. And so that's beyond classical textbook, which is it's recent research, a recent research result in these original slides of a colleague. So he was presenting this talk in Nice, and of course there were some things about motivating this TSP, and yeah, so there's something about shortest tours, shortest paths you can compute, and you can compute that, and well, okay. What happens if you want to visit all of those, do a shortest round trip, and that's of course the traveling salesman problem. I've talked about that. And here's a book, a really nice book if you like the traveling salesman problem, if you want to learn some more history and other things about this. I strongly recommend this book. It's not even very expensive. It was written by Bill Cook, good friend and leading authority on the traveling salesman. He was one of the driving forces behind this exact methods, and he's got the best code for solving TSPs to prove them optimally. And he also writes nice books. So that's one thing I strongly recommend in pursuit of the traveling salesman. Okay, here we go. So he says, okay, Hamilton paths, somebody mentioned here, Maurice was talking about Hamiltonian path. Kirkman already in the 1800s. We saw that it's actually older, 3,000 years ago, Odysseus was trying to solve some. Benchmark problems in computer science. So I was talking with Drosophila and all this, probably the most studied NP-hard computational job, not computational geometry, optimization problem. And it is exact algorithms require exponential time, worst case, and all these sorts of things. So it's a major open problem with efficient computation and so on. So yeah, approximation algorithms, right? So there are a few things you could to use heuristics. So mind you, these are not my slides. Thank you, Ola, for letting me use them and share them and show them. And so there's something about, yeah, maybe bad instances don't happen too often, and you can do some things. So you see here, this is way back when Danzig, Fulkerson, and Johnson solved in a 48-city instance in the US. 48 is, of course, all the capitals of the continental states in the US, minus Alaska and Hawaii. And then this went up, and you see, so I showed you the post offices in the US. There's one instance which is a little bigger, so the same group, Applegate, Bixby, Schwartel, and Cook. And then, of course, another colleague here with a 978 cities in Sweden. And that is really pushing the limits, because as Ola, you can infer from his name, sounds Scandinavian, is Scandinavian. So Sweden only has 9 million inhabitants. So, we're looking at really, really small places, 360 persons per city. There's some bigger cities like Stockholm and Göteborg and so on. So you're really looking at then basically milk cans and little huts and whatever in the woods. That's about as far as you can. There are bigger benchmark instances, but of course, so much. Now, of course, we're talking about approximation algorithms, and maybe we can find a reasonably good solution in worst case polynomial time. And so that again is of course this. And you see that was a survey for a general cutting edge scientific audience. So introducing that is something you should feel comfortable and good about. So if you have an approximation factor of 1, then you have an optimal solution because that is the same in the numerator and denominator. And 1.01, then you're 1% worse than the optimal. That's really good. And let's not worry about these cars, but keep going on this. You saw Christophidis, 1970s. I just showed you how that works. And Held and Karp had something which is related to linear programming, and there's something, I won't talk about linear programming here, but there's something behind it which says like, yeah, this is 1.5 and this Christophidis has something to do with it. And there's some relaxations of solving some problems, modeling some of these graph problems as linear programs and solving the relaxation where you're allowed to use fractional edges and so on and so on. And 1980s, nothing has happened. And this is important. 1990s, late 1990s in fact, Sanjeev Arora and Joe Mitchell independently came up with p-tasks for the Euclidean TSP, and you will see this, learn this next week by Joe himself. So I can just look at that and say, when these points are points in a geometric setting where you have Euclidean distances, points in the plane, shortest distances, geometric distances, then you can approximate it arbitrarily well. Or in other words, for every epsilon, there's a 1 plus epsilon approximation algorithm, which is polynomial in n. And for fixed epsilon, it may be exponential for 1 over epsilon, but that's another thing. So here, straight line distances. And there's a few things, a few expansions, planar TSP, if it's a graph that can be embedded in the plane, some of the same ideas using a subdivision recursion. We'll see that next week. Works well. Now, on the other side, this is something we don't talk about much, but on the other side, there's some lower bounds on the traveling salesman in metric. So triangle inequality, you saw why triangle inequality is important for approximation. You can show, it's not hard, not difficult, from Hamiltonicity of a graph, that if you don't have a triangle inequality, then approximating is hopeless, because you could look at weights in a graph where you put a 1 down if it's an edge in the graph, and if you have a Hamiltonian cycle, you get a tour of length n. And if you don't have a Hamiltonian cycle, you put edge lengths of something really, really big. And if you need to use one of those edges which are not in the graph because you don't have a Hamiltonian cycle, you get at least one really, really, really big edge, and then the whole thing is really expensive. So without triangle inequality, hopeless. But here is a result that says, well, you know, if you have the triangle inequality, but not in the plane, not geometric, but you have some general graph with distances and so on, they obey triangle inequality. But you can do a few more fancier things than with geometric distances. Then it turns out there's a lower bound on the approximability, 220 divided by 219. So if you want to get closer than that, you have to be able to solve it exactly. There's a lot of much deeper theory behind it, and they showed, hey, there's a bound in the 2000s. So there was some improvement in the last 10 years, 9 years ago. Slightly improved, slightly simplified, slightly better lower bound, but I will not talk too much about it because that gets us into completely different terrain of complexity and how to prove these lower bounds. So the question is, you look at this and you say, okay, 220 over 219, yeah, we can do that. 1.5 is Christophidis, and 4/3, there is this hard-held carp, which comes from linear programming, and there's something going on here, we'll see that in a second, where 4/3 seems to be a natural lower bound, like for some of these graph algorithms to get a better bound, and people believe, yeah, that should be like the real lower bound, not this, what you can prove, but that. So there's nothing happening here between 1.5 and 4/3. And when he said today, of course, that was when he was giving this talk, which was in a few years ago. So can we do better than 1.5? And one thing to look at is not geometrically embedded points, which is what Joe will talk about next week, but a graph setting. And the graph setting is, it's not the completely general problem, but it is still general enough. So you're giving an unweighted directed graph like this, and the distance between two of these vertices is not an arbitrary number that satisfies triangle equality, but it is the shortest path in this graph. So when you go from here to here, like from here to here, you see this is 1, 2, 3, 4. And if you take that path, it's 1, 2, 3, 4. And if you do a 2 detour, it gets 1, 2, 3, 4, 5. So the shortest path between this vertex and that vertex has length 4. So the cost of going from here to here directly, the edge here, which is not drawn, is that length. So you see the shortest path between U and V in this graph G. So that's a graph TSP problem. And so you see here, there's some paths. And oh yeah, so here's a Hamiltonian path, not a cycle, but a path. That's nice. And vertices, length n minus 1. And if you want to turn that into a tour, you need to add one edge, which has length 4. And so yeah, it's not a Hamiltonian cycle. In fact, you can look at this and see like, oh, is there a Hamiltonian cycle? In fact, there's not. Why not? Because you have this triangle on this side, you have that triangle on that side, and you can think of having maybe even more in between to sort of make it really clear. And so when you follow one of these paths, you cross from one triangle to the other side, from one island, triangular island, to the other, and you go up, whoop, whoop. But a closed tour must go across this set of bridges an even number of times, but there's an odd number of these bridges, and so you cannot avoid crossing this somehow an even number, so you must cross something multiple times. And in fact, you see there's 3 of those, and you must cross each of them to sort of visit these points or back up. So it's sort of plausible that there will be a 4/3 here somewhere. So like that. Now, you could also look at this edge, which turns out into a Hamiltonian cycle, by basically looking at the corresponding path. Okay, so you're duplicating some edges, and you will see, yeah, this is somehow, again, something Eulerian, right? So there's something going on. All right. So the cost is the number of edges here. So how many edges do you need to turn this into an Eulerian multigraph, which spans the whole thing, and how much does that cost? So same thing again, we had this before, lower bound 1.005, Christoffel is 1.5, and there's this natural held card bound, which says 4/3 is probably what you can hope for. And then in 2005, Gamarnik, Levenstein, and Svirdenko showed that there's a 1.487 approximation for cubic 3-edge connected graphs. So there's something going on. And Boyd, who's actually an academic sister, Sidis van der Star and Stauchi in 2010 showed 4 cubic graphs. Cubic graphs are relatively special because they are, everybody has degree 3. And when you find a tour in a graph that has degree 3 everywhere, there's not too many chances, right? Choices. I mean, you have to pick 2 out of 3 in each vertex, and where do you leave, where do you enter? That's basically it. But it's still hard, but you can cubic here. And so you can improve that. So they push this further and says, oh, yeah, we can get this 4/3. And subcubic, there may also be some vertices which only have degree 2. A degree 1 vertex is not so interesting because, I mean, you enter it and you leave it through the same edge. So degree 2, degree 3. So there's something going on. So having these is a little nastier. There's something going on with the metric. So there was this frozen automobile. And so what has happened? What happened with cars since 1976? So there's been, no, phones. Let's look at phones. I think phones are better. So in 1976, you had this kind of phone, and then you go and you go and you go. And then in 2010, you actually have something like a smartphone, and that still continues. And what happened in for the speed of approximating traveling salesman, I should say not the speed, but the approximation factor. So it's been 1.5, 1.5, 1.5, and now we're at, it was 1.487. Now there's been some improvements since then. So as I will wave my hands over this, 1.461, and a little bit more, 1.444, and something like 1.4. And the question is, can you get to 4/3 here, or maybe even below that? I don't know. Unlikely, but what's going on here? So there are a number of different ways, and I will not run you through all of those. Some of them are a little trickier, but there are some basic ideas on this whole thing. It says sampling spanning trees. So remember, Christophidis was doing a spanning tree, computing a spanning tree, and then using a min-cost matching on the odd degree vertices. And we saw if you use the wrong spanning tree, like in this comb zigzagging example, if you use the wrong spanning tree here, then you get a 3/2 or 1.5. But that is because of a poor choice of a spanning tree. So the idea is use not just one minimum spanning tree, but look at several minimum spanning trees, because there's more than that. So here, that reminder that I showed you that beforehand. So that was that. So that tight example, again, showing it. So far, so good. So you see here, there's this n/2, and that gives you 3/2 times n. So instead of using a minimum spanning tree, use a different kind of spanning tree. And so here's a bit about this held carp thingy. This held carp thingy uses linear programming. So what's the way of modeling this? You use variables on the edges. So every edge is in or not. And if you have a set of edges, then there's, of course, the edges used or not, and then there's the length or the cost of the edge. Remember, this is the graph TSP, where this is like a distance in this original graph for that edge. So it's a cost for that edge. And there are a few properties that you need. You want, for n vertices, you need n edges. So the total should be this. So sum of all these variables for the edges comes up to n, or cardinality of the vertex set. And then there's this other condition here that says, for every subset of vertices, for every proper subset of vertices, the set of edges that stays within the set must be less than the cardinality of these, because if you have a set of edges within a non-trivial set of vertices, that must close a cycle, because a tree within this set has one less than the number of vertices. So it has to be, it cannot have a cycle, which is a way of saying, yeah, it has to be tree, that you cannot have any cycle in this. There's another alternative way of doing this. Instead, you could say, for every proper set of vertices, there has to be an edge leaving that set to connect it to the rest of the other vertices. So that is a combinatorial characterization, and you see here there's not zeros and ones, but it says, well, you just have some degree, some variable value which is more than 0. So you could have some which are not integers. So that's a tour, contains that number of edges, and there you want to avoid subtours, frowny face here, so that has some subtours, and you see that this is not connected, so you don't want these subtours. These are called subtour constraints, and there's an exponential number of them because you have an exponential number of subsets. So from this is a linear program. You can compute that in polynomial time, and yeah, there's a description of this set of extreme points of this linear program, and that you can take something from here, and what you can then look at is how you can get spanning trees from this polytope. So there's something slightly deeper going on which goes beyond the content of this lecture. For those of you who have not seen linear programming and studied in more detail, I don't want to sort of get on this huge tangent, but I want to at least show you that there's some connection to linear programming where you get some results out of this relaxation. And if you do that, then the cost of a spanning tree, you know it's v minus 1. And then there's some vertices here. If you look at this, I mean, there are different kinds of spanning trees. These are odd degree vertices. You see, if you look closely, you see that's a degree 1 vertex, that's a degree 1 vertex. That is a degree 3 vertex, that's a degree 1 vertex. So if you look at the spanning trees in this here, and then you look at these matchings here, you get this kind of thing, okay? That's an upper bound, and yeah, that's Christophidis, of course, again. But depending on these sum of the structure, because for getting it tight for 3/2, you have to be unlucky. And if you sample and if you look at the probability on this, and that again is another topic, so linear programming is one where I point at. Some of you may have seen it, others may not. It's not required. And then there's something about analyzing that distribution, which is another thing which I point at, and fewer of you may know something about probability there. But you can argue something about the expected value. And if there's an expected value which is less than 1.5, then there must be some structures which are less than 1.5, and that allows you to do something better. So there's something, a parallel track, and again, I will sort of give you an idea. The same idea is you look at this Christophidis, and you try to do better than just some spanning tree and say, okay, this is a spanning tree we have. There's something, you look at the structure of this whole thing, and you try to work with that and improve that. So here's the thing. There's a bit, so this one thing that you just saw where I waved my hands over the linear programming was more mathematical optimization, abstract, non-integer weights on these, and then you do the linear programming analysis, you map that, and so on and so on. And there's something where you look at more of the combinatorial side, of more of the graphs and the edges. And for some of you, including me, that maybe somehow feel more natural or more hands-on rather than having this polytope of minimum spanning trees. And so there are some things where you can get, for special graph classes, some graph theoretic results which then give you better approximations. So, like I said, there's hand waving, but the idea is to give you an impression. You don't have to learn this for the exam in detail. You don't have to prove these things. Of course, there's all the original papers that tell you some structures of some of these graphs. So special graph classes have tours which are cheap. There's the 4/3 again. And so if you look at one of these and you see, I mean, these are cubics, okay? You see that's cubic. So you look at perfect matchings in here. And if you look at this, I mean, cubic means that every vertex has three vertices, three edges, sorry, three edges. Cubic, cubic, cubic here. And if you take each edge with a probability of 1/3, you get something like a matching. Now, there's some structure behind this, and you can look at all these edges, and then you add something, and you sort of get the feeling like, yeah, there's something relationship to matching, because if you have everything with a probability of 1/3, that means for every vertex, one of its three edges gets picked with probability 1/3, one of them, and you can at least intuitively see that in the end you want to have a structure which has one edge for each vertex, so it's sort of plausible that you get 1/3 of these, 1/3 of these edges. There's of course a little bit more to it, but you sort of see that it's plausible if you take all these edges and you have 1/3 total weight here, that you get a total of something like 4/3 that. And yeah, then maybe you get such a matching here, 1, 2, 3, these edges. And so there is a conjecture which says that any cubic edge-connected graph, now there's something about the connectivity here. Edge-connected means, of course, that you must remove at least two edges to disconnect this whole graph. And that makes sense because if you travel this, there must be two ways of connecting different subsets of these vertices. So that's a really natural class. There's this unproven conjecture that any such graph has 6 matchings so that every edge appears in at most 2 of them. So there's some fancy graph theory, some deep graph theory going on. And of course, if you have 6 matchings to cover each edge twice, then you see 6, 2, that has something to do with this 1/3, so there's some connection here. And that gives you some idea of how this could turn into 4/3. Yeah, so you get this, and then of course, then you have 4/3 of the edges, and then, yeah, okay, sure, get a tour, do the shortcut thing again, and yeah, get the 4/3. And there's that. So that is a 4/3 for this special graph class, and that's some idea of how to tackle this. So of course, one idea is that instead of adding edges from matching, you remove some of them, because in the end, you want an Eulerian graph, and if you can remove some instead of adding some, even better, because that's cheaper. So that's another idea, and that's something that has been pursued, and I will quickly click over this because this goes beyond some of these things. So here's something removed, and when you remove, of course, it's plausible, and this will end up being cheaper. And of course, you want to analyze that in more detail. So of course, you can't just remove anything because it needs to stay connected. So there's a bit of finer points, finer issues here. And yeah, so try to do that with more care, removing some of these edges. And yeah, you may get something different here. And there's some more results here, and you get a tour of a certain length. You see there's, if you do the math here, that looks like 4/3, but it is actually less than 4/3 of the edges, so there's some 2/3 of the vertices, which is less than that. And then if you increase that, you can fiddle with that and do a bit more graph theory on this. And like I said, just click over this and wave my hands over this. So there's a lot of deep stuff going on. It's world-leading people working on this for many years in a hard way. But it gives you an idea of how this can be done. And I will just do a few more pointing at some of these nice figures and some of these ideas, analyze what the graph structure does, and how you can improve and work with that. So, so there's something which is removed, and then you can get some from this, some ways of doing this better. And if you look at this carefully, you get better approximation factors. And so there's some results like Svensson did 10 years ago. And yeah, let's not worry about that. And there's, of course, some more things that are happening here, how you can do this and what works. And then there's a bit more of these working more details, finer and so on, and getting this 1.5 to 1.461. See that? And different approaches, 1.458. So you don't have to remember the details of how they did this, but the fact that there was some really, really, really small improvements. I mean, we're going like a 0.003 in improvements, and that's getting really, really fancy here, doing lots of stuff to get below 1.5 and push this. And something here. And 4/3 is sort of the ultimate price, which is, and I will not worry about that, and I'll skip over that and skip over that, because I think I've shown you enough to give you an idea, and there's a few more fancy ideas that work here. Yeah, so that's where things were at this point, and you can sort of imagine this was 1.33 for these special types of graphs, and that is general metrics, yeah, and so on and so on and so on. Some of these conjectures, state of the art, more things, but let's leave it at that. 4/3 is sort of a natural lower bound because of this. 4/3 shows up and shows up again, and it has something to do with these examples. Triangle on this side, triangle on that side, and these paths across, which deduplicating. Yeah, so cubic graphs are really difficult, and we've seen some of these things here. And yeah, let's not worry about these. There's a lot more fancy stuff. So there's been some progress by really, really getting down and dirty on these graphs and looking at this Christophidis again and doing things slightly differently. But if you take away something, it's that sometimes people spend a lot of time, really smart people, many years to get from 1.5 to something like 1.461, and are still working on this to get this to 1.33, which is still a far distance away from 1. And that's that, and that's that, and with that, there's that. So thank you. Oh, that was a little too quick. Here we go. Thank you for listening. Thank you for staying here. And thank you for Ola Svensson for letting me use his slides and references here. That's it for today. Thank you. And next week, I'll share that in time. It will be actually a Zoom, not a YouTube. It will be Joe Mitchell's Zoom, so we're guests with him. We're not using Zoom ourselves, but we're watching him on his Zoom, on his slides and his talk. And I'll share that in time. Thank you for now, and see you around and soon.